One particularly practical way to use exponents is in what we call scientific notation. There's scientific notation for very large numbers and scientific notation for small numbers, but we're only going to deal with the large numbers in this course. Scientific notation has to be written in a certain way. We're always going to have a single digit followed by a decimal point, followed by any other significant digits, and then times 10 to some power or exponent. That's the form that scientific notation always takes. This number right here is a single digit, meaning it has to be between the numbers 1 and 9 and is not itself a decimal. So this could be a 6, or a 4, or a 1, or a 7, but it won't be a 0, and it won't be, say, 11. It has to be between 1 and 9, including 1 and 9. Here are some examples of numbers in scientific notation. 3.624 times 10 to the 2. 8.107 times 10 to the 19th. 1.6998 times 10 to the 10th. 9.107624 times 10 to the 100. The exponent can be any number, small, medium, or large. But notice that in each case, the number in front of the decimal point is a single digit, something between 1 and 9, including 1 or 9. So why do we use scientific notation? Well, some numbers are very large, like the number of miles from Earth to the Sun. Here's a fairly large number. It's not enormous, but it's pretty big. If I want to write this number in scientific notation, I need to make sure that the significant numbers are displayed so that the first digit is followed by a decimal point, and then other significant digits follow. But then I have to write times 10 to some power. How do I figure out what the power is? Well, to get this number, 3.76, to look like its original form, I would need to move this decimal point 1, 2, 3, 4, 5 places, and then fill in the blank spaces with zeros. So that means that my exponent is 5. Let's back up a little bit and see how this really works. So these are numbers in scientific notation, but what does it mean? Scientific notation is a standardized way to write large numbers. The number 10 to the 2, which means 10 times itself 2 times, is 100. So writing 3.624 times 10 to the 2 means 3.624 times 100. Whether you do this on paper or on your calculator, you'll find that the answer to this small arithmetic problem is 362.4. What's happened is that the decimal place has been moved from here, its original location, over 2 places. Let's look at one of our other examples. 10 to the 10 is 10 times itself 10 times. If 10 times itself 2 times gives us a 1 with 2 zeros, then 10 times itself 10 times will give us a 1 followed by 10 zeros. So 1.6998 times 10 to the 10th is like saying 1.6998 times whatever that number is. Let's see, it looks like 10 billion. When I do this, either on paper or on my calculator, the result will be 16998 followed by 6 zeros. And the result is the same number, 1.6998, with the decimal place that's been moved from its original location over to the right 10 places. 5, 6, 7, 8, 9, 10. So, multiplying a number by 10 to the 10 moves the decimal point over 10 places. I don't think I'll do this one if you don't mind, or this one. Those numbers are pretty big. But that's the point. I can write a really big number in a fairly small amount of space by using scientific notation. Let's take a look at another example. Let's write the number 3.52 times 10 to the 5th. Currently in scientific notation, let's write it in decimal notation or standard notation. Currently my decimal point is here. There's only one digit to its left. 3.52 times 10 to the 5th is the same as 3, and then move the decimal point 5 places to the right. 1, 2, 3, 4, 5, and there are no numbers there, but I'll just add zeros. Because I could have written this 3.52 as 3.52000000. I can write as many zeros here as I need. So since these zeros can appear at the end of any decimal number, they're there even if they're not showing. So here are the first three after my 3.52, and I just need to go back in and make them visible after I've moved my decimal point. So 3.52 times 10 to the 5th equals 352 followed by 3 zeros, which is 352,000. What about taking a really large number and putting it into scientific notation? The number 5,162,000 can be written in scientific notation by rewriting it so that the decimal point goes right after the first digit in the number, followed by any significant digits. And by significant, I mean not zeros, or not trailing zeros anyway. So 3.162. And then times 10 to some power. What's the power? Well, if I were writing this number in this form, I would take the decimal point and I would move it over to the right. 1, 2, that's the question, isn't it? How many decimal places do I have to move it? I have to move it enough decimal places so that I get this original number back. And since I'm starting with my decimal point here in this position, I would have to move it 1, 2, 3, 4, 5, 6 places. So in scientific notation, the exponent is a 6. Let's try another one, just like that. How about the number 2,160,000,000? Okay, first of all, let's find the position for our decimal point. It has to go in this position here when I start to write out my number. So I'm going to have 2 point followed by any significant numbers. Well, initially I have a 1, and then I have some zeros, but they're not trailing zeros. I have some other numbers in here as well. So I need to write all of the numbers up to the point at which anything after that is a 0. So I need to write this piece after my decimal point. I've already got the 1 and then 0, 0, 1, 6. And then I can stop writing. Now, how would I get this number from scientific notation back to decimal notation? In other words, from here, how many places would I have to move my decimal point to the right to get it back in this form? Well, going back to this form of the number, my decimal point went in this position here. So starting from that position, if I count 1, 2, until I get to the end of the number, that tells me how many places I had to move the decimal point. So that's going to tell me what the exponent is. I started 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places. So the exponent is a 12. One of the nice things about scientific notation is that numbers in otherwise very different size formats become standard in their size, in their format. So I could multiply 5.162 times 10 to the 6th times 2.10016 times 10 to the 12th, simply by using the commutative property of multiplication and some exponent rules. This is times, although it's not in the format that we've been using. Here, let me change the color so it's easier to see what's going on. That's a times and that's a times. But this is a times as well. So what I really have here now is 5.162 times 10 to the 6th times 2.10016 times 10 to the 12th. Using the commutative property of multiplication, I can rewrite this problem as 5.162 times 2.10016 times 10 to the 6th times 10 to the 12th. This multiplication I can do in my calculator. I get 10.84102592. This I can multiply using rules of exponents. The same base, 10, to the power of, well, I have 6 copies here, and I have 12 copies here. These are all multiplied. These are all multiplied. 10 times itself, 6 times. And those are multiplied by those. So altogether I have 6 plus 12, or 18 copies. Now, this number is not in scientific notation, even though its original form was scientific notation before I started doing the multiplication. To be in scientific notation, my decimal point would have to be here, not here. So if I rewrite the number 1.084 and so on, then I can't just rewrite the 10 to the 18th. I've taken a number not in scientific notation, and I'm trying to put it into scientific notation. If it were in scientific notation, how many decimal places would I have to move the point so that it was back in its non-scientific notation location? I'd have to go one more decimal place to the right. So although I started out 10 to the 18th, in scientific notation, this becomes 10 to the 19th. So just taking a large number and putting it into scientific notation is one skill, but being able to take a number that's almost in scientific notation and put it into scientific notation is another skill. We're mostly going to be focusing on just converting numbers back and forth in this class, But I did want you to see, first of all, that you can perform operations on numbers in scientific notation. And I think that it's easier to do that than to work with the very large numbers that they represent. Not only that, but sometimes the result is close to being in scientific notation. And if your problem is in scientific notation, your answer should be as well. And in this case, I had some work to do before I actually got it there.